Thank you, host. Thank you, everyone. Welcome, experts and guests, to the afternoon session. Today, on behalf of FaithTech, I would like to present a solution overview of 5 key AI power test scenarios. This talk will take 25 minutes. Thank you for listening. First, a brief introduction to FaithTech. FaithTech celebrates its 20th anniversary this year. Personally, I have been in the industry nearly 30 years. Our parent company is King Cable Group, a controlling shareholder of FaithTech. I joined back in 1998. We are in the test and measurement sector, serving the power industry if power companies are selling shovels. In the AI era, we are selling the water, standardized measurement solutions, right? That's the role. And it's a very important one because calibration, measurement, simulation help clients pre-evaluate real operating conditions in future AI power and computing scenarios for early validation and stress testing. In this way, providing strong system-level solutions. At FaithTech, our core expertise is DC power supplies and electronic loads. Over the past 20 years, we grew with Shenzhen's power electronics. We also saw many industry transitions. Our clients evolved from PC power supplies, server adapters, to power tools, and later EV powertrains and UPS systems, from battery systems, onboard electronics, UPS, power modules, to PV inverters. All along this journey, we served all these industries, accumulating rich application experience. Last year, FaithTech was recognized as a specialized, refined, unique, and innovative little giant enterprise in our past application cases. We have delivered many representative solutions. Here is a summary of some of these. I remember Mr. Ren, the CEO of Huawei, once said, "Huawei has been attacking a single gateway for decades, building a very deep technical barrier." And for FaithTech, in our power supply field, we adopt the same strategy in power testing. Therefore, in this process, we have also developed many typical application solutions. Here are a few summarized ones. For example, we once provided a dedicated low voltage, high current load for China's hydrogen fuel cells. And these technologies will play a key role in the AI power computing scenarios I will discuss next. Similarly, for aerospace fuses, aerospace-grade fuses and circuit breakers used in China's Tiangong space station, we have provided 10,000 amp level fuse testing systems. Similarly, for nuclear fusion, superconducting coil power supplies, and European superconducting nuclear fusion experimental laboratories, we have provided systems exceeding tens of thousands of amperes domestically. For power batteries, we offer not only charge and discharge testing, but also cell simulation. We perform high capacity charging and discharging, as well as high-precision cell simulation testing for very small batteries, for domestic DC electric propulsion, involving some military applications that we cannot discuss in detail. We have conducted Megawatt-Level system tests for DC electric propulsion motors in submarines and ships, also for our many charging module customers in Shenzhen, who need very rigorous overload and overcurrent tests. We have provided complete solutions. These solutions were built over a long period. As the current wave of AI power supplies arrives, we found the customer demands were fully met and solved by our past achievements, even exceeding expectations. Next, I will discuss these challenges and our solutions. We divide AI test scenarios into 5 categories, of course. They can be further subdivided, but from our current perspective, these 5 areas basically cover it. The first is the core driver of AI computing power, which is NVIDIA, in their computing power, GPU power supplies. The mode is different from traditional CPUs. It has large power consumption, large surges, and huge current demands. Thus, it poses major challenges to the front-end power supply. Since this wave arrived, it has driven leaps in related industries, as many in the industry know, and experts said that in AI data center investment, over 50% of consumption is electrical power. This is closely related to everyone. In addition, there are signal transmission, optical communication, memory, materials, and so on. Let's keep it simple. So it drives our entire industry. The second is the DC busbar that carries large currents. This is also a highly specialized field. The third is a topic of concern under the current HVDC 800 volts plus or minus 400 volts architecture. How our power supply cabinets, namely the power shelf and rack built from modules, can withstand megawatt-level validation to meet industry specifications. This poses rigorous test requirements. The fourth is PSU testing, which is also very familiar to us, since megawatt-level systems are ultimately stacked from individual modules in future mass production testing. Testing of a wide variety of modules will eventually be popularized in manufacturing. The fifth is our backup battery system. As it evolved from lead-acid batteries in traditional UPS to lithium batteries plus supercapacitors, the requirements for backup power are actually our previous requirements for battery charging, discharge capacity, and cell BMS management. So we summarize these 5 scenarios. I will now expand on each. As everyone knows, the first point is GPU testing. In the evolution of GPUs, it is well known that as GPUs grow larger, they take up more board space. Thus, board space efficiency is compressed drastically. Therefore, they package components as much as possible, such as 3D packaging, vertical power delivery VPD, and multi-layer stacking. Currently, with HBM multi-layer stacking regarding power delivery, it transitioned from lateral power delivery, LPD, to the current VPD mode. This approach reduces current losses. However, it causes large peak currents and surges. I remember an interesting case. Nearly 5 years ago, NVIDIA approached us to evaluate one of our products. We found it quite surprising at the time. In the past, NVIDIA was just a graphics card company. I treated graphics cards like standard CPUs, handling small signals. So I asked them, why do you need such high current? They said, we have a product now whose peak current might reach 1000 amps. And while drawing 1000 amps, it must run at full current at low voltage. It must carry full current at 0.2 volts, reaching 1000 amps, or even 2000 amps. So they asked, do you have such a product? We searched all suppliers worldwide, including some famous major brands, and none could do it. I said, we can, because in the hydrogen fuel cell industry earlier, we had already provided clients with loads simulating PEM zero voltage and negative voltage startup up to 5000 amps, they said. Great, let us have one for a test. After the test, they said it met their requirements. So later, as you might have seen last year, NVIDIA required 8 gallium nitride manufacturers at its GTC conference, now 14, to strictly comply with this test standard. Our equipment is used by many of these brands that have come here today, such as Renesas, TI, and Rome. They are all here. They all use our equipment to test the GPU power modules. We are the supplier. In this case, the requirement is low voltage with high current. Among the products we supply to them, there are several series tailored to different test requirements. And in this area, it is still evolving. We just received the latest requirement for the current PSU modules. When stepping down from 48 volts to 12 volts to enter the GPU tray, They now require us to provide 0.3 volts at 5,000 amps, with load requirements reaching a current slew rate of 100 amps per microsecond. Next, it will enter mass production testing. Regarding this demand, our current capabilities meet their requirements. This will be realized in a year or two. Since our products are different from component manufacturers who introduce detailed lists, as an R&D testing instrument manufacturer, we provide capability. Because testing has its own specifications, and these specifications are your standards for access, our equipment ensures tests match specifications with 100% compliance. This is the capability we provide. The second area is the copper busbar inside the cabinet. There is a saying, optical in, copper out. But what does it phase out? It phases out copper connections for high-speed signals. But for our current busbars, it remains the core equipment. As for this part, the current copper busbars in NVIDIA systems and sidecars carry massive current. Due to the operating characteristics of GPUs, they burst large currents. Under light load or stable conditions, it might only be 3,000 amps to 5,000 amps, but once it enters burst mode, it might peak to 200% or higher. Therefore, achieving currents above 15,000 amps is a project that must be guaranteed. In this area, previously, FaithTech supplied power for superconducting coils. Each coil path requires 10,000 amps for core coils. It even goes up to 20,000 amps, so we reserve this technology for years. Ultimately, the test execution is very straightforward. We offer two solutions. The first is the direct short circuit method. This connects our high current supply directly to the bus bar, injecting current exceeding 15,000 amps directly. Under this condition, thermal imagers or sensors inspect heat at each connection, identifying hot spots in a timely manner. This is the first solution. Not only do we provide high current, but we also simulate pulses for cyclic testing. The second method is dynamic source loading. In this method, the front end is a unidirectional source simulating our HVDC 800 volts. The back end is a source simulating AI load. The middle is the copper connection part, forming a fully simulated loop. Each PSU path is simulated by one of our power supply modules, the front end and back. And the modules fully simulate the actual conditions of NVIDIA or OCP modules. It dynamically tests the copper bus bar for each path. In this way, it can execute a perfect simulation. It completely simulates NVIDIA's real-time data. Then, under this condition, it combines with the static method mentioned earlier to compare the two, forming a complete R&D test requirement. Thirdly, regarding the megawatt-level testing that everyone is concerned about. Currently, there are two routes in the industry. Let's summarize the two mainstream routes. NVIDIA is like Apple, while OC. P is like Android. NVIDIA takes a closed route. It emphasizes independent certification. Only shortlisted vendors can cooperate, so it lists many suppliers for each product. For gallium nitride devices, there might be 10 to 14 companies for optical communication, BBU modules. And copper connections, it has strict qualifications. OCP, on the other hand, is open. It only sets standards. Anyone meeting and validating standards is welcome, eventually forming an open alliance. They operate in this mode with major North American CSPs. So differences exist between the two. For instance, NVIDIA is 800 volts, while OCP is plus minus 400 volts. For NVIDIA, its power supplies, BBUs, CDUs, and computer trays are integrated in a rack for high efficiency, high density, and high power. For OCP, its power supply is placed in a sidecar separating the power rack. So they differ in form, but from a test perspective, their test requirements are similar, though NVIDIA definitely demands more. For example, among the core requirements, the first is megawatt-level loading. For us as load makers in the past, we only needed to match power with the client's DU. T for charging module customers in Shenzhen, ranging from 20 to 60 kilowatts, now 80 kilowatts, and 120 kilowatts in the future. The load we provide only needs to match 1-to-1 or be larger to leave some margin. However, under NVIDIA's requirements, your load must parallel for cabinet testing. This means expanding our load array to reach megawatt-level testing. The difference between standalone and megawatt-level testing lies in having extensive paralleling control and current sharing capabilities. At the same time, for high currents, you must resolve inductance effects on the current slew rate. So connection requirements are extremely high. These aspects of ours are verified by leading manufacturers. We can guarantee a standalone current slew rate of 96 amps per M microsecond and reach 150 amps per M microsecond after paralleling. This indicator is the touchstone of current verification. Secondly, when dozens of machines are paralleled, high demands are placed on sharing and balance control. Once synchronization performance goes out of control, it might cause major accidents. Similar incidents have occurred in the industry. So this has high requirements. Paralleling is a key divider for system vendors. Regarding high-speed response, the current standard of 60 amps per M microsecond is the entry standard. If you cannot achieve this, you might barely pass verification this year, but by next year it might be obsolete. As test standards grow daily, everyone must look further ahead with a 2 to 3 year expectation for the return on investment to be controllable. Thirdly, EDP. P-testing requirements are extremely high. It requires overload testing for 180% overload, maintained for milliseconds, 0.5 milliseconds at the shortest, and 2 to 3 milliseconds at the longest. Meanwhile, it must offer high frequency load pooling from low load to high load to form a frequency conducted regularly over a long cycle. So this work demands very high overload capability from our loads. In this regard, through collaboration with charging module clients, we are fully confident. Why historically? Charging module tests require 200% load pooling. During load pooling, you need second level capability. So our load capability is at the second level, non-milliseconds, which is 1,000 times longer. This is the result of working hard with our peers in the past. For megawatt level solutions, I will skip this page quickly. We provide 3 solutions for megawatt level setups. Please note there are 3 solutions. We have seen that in megawatt level systems, testing requirements have diverged significantly based on scenarios. Some leading manufacturers are willing to invest heavily in systems with the strongest capabilities without requiring regenerative energy. We employ our best dissipating loads, namely high-speed loads, to meet requirements. The capability it offers can achieve up to 150 amps slew rate and 200% overload for several seconds. But its drawback is that it cannot regenerate energy. It is a system purely used to verify extreme capabilities. The second system is for burn-in and lifetime testing of modules. And lifetime testing, its testing requirements reduce functional verification, but require efficient energy savings for regeneration. So its 94% regenerative efficiency allows burn-in for days to verify lifetime capacity. Under this condition, its efficiency to cost ratio is the highest and the cost is the lowest, but both solutions have their own drawbacks. The first has high performance. no regeneration. The second meets basic performance requirements, but features regeneration. Now, many customers request both. I need performance and energy regeneration. This poses high demands on us, so we provided the third solution. This is currently widely welcomed by system-level customers, and they started evaluation recently. Clients like Eaton and Vertiv have evaluated prototypes for their subsequent BBU and Megawatt-Level sidecar testing. They will choose this solution first. Its feature is ensuring our tests meet all OC. P-test requirements. First, the parallel slew rate can reach 40 amps per M microsecond. Second, it sustains 180% overload within 3 milliseconds. Third, it can perform 10 kilohertz cyclic pulse loading. These three core indicators represent its capability. Meanwhile, it offers 80% energy regeneration. This means when conducting megawatt-level testing during long-term tests, your grid environment requires no additional modification. You only supply 20% of the power. For 1 megawatt, you only need a grid environment of around 200 kilowatts to achieve it. So this is very user-friendly for many customers. The parameters below represent its core specs. These three solutions have their own different scenarios. We prefer R&D high-performance loads, regenerative ones for burn-in testing, and the third one for compliance testing. Currently, we are collaborating with testing organizations who are interested in partnering since they receive requests from many customers wanting to enter this market, but are hesitant to make large capital investments. They will outsource to third-party testing. The fourth is PSU modules. As everyone knows, there are two mainstream architectures and two domestic standards. For domestic, the mainstream is Alibaba's Panama. Huawei's Ascend is also gaining strength. However, for Panama, since Alibaba Cloud has the largest coverage, its market share is the highest. It includes many testing requirements. So for PSU power levels, its inputs and outputs, test requirements and power capabilities differ with over 100 variations. So the variety is immense, but for us, it is not complex, as one of our series can meet all these needs. In this series, we have high speed and low speed options and different power levels. A single unit can reach 72 kilowatts basically. The vast majority of categories can be tested by a single unit. So it is a single machine solution covering the entire industry's PSU architecture. Secondly, for this product, we have achieved compatibility with some mainstream automation systems in the industry. As everyone might know, in the power industry's automation systems in the past, a Taiwanese brand was widely used. Our load is fully compatible with it, meaning direct replacement and use. The final scenario is BBU testing. Actually, it is somewhat unique. For example, namely that it must be capable of high power discharge and must simulate ORV, the requirement for BB. Us is that when the bus voltage of your entire rack, such as megawatt, level drops below the monitored voltage, your BBU must intervene immediately. And when it intervenes, it must sustain power supply for 3 minutes. For 3 minutes, our backup diesel generators will start for secondary response. So BBUs are highly critical in current backup power systems. They use lithium batteries. It must meet high power validation and cell level simulation. This requirement happens to align with a market we accumulated in the past for one of our past products in current domestic BM systems, such as battery manufacturers like BYD EV Energy and Guoxun High-Tech. Among these BMS vendors, they use our cell simulators extensively for BMS management. So this technology also happens to be in our lineup. It is a niche product. Previously, as load makers, we only focused on medium to high power, while microamp level simulation for small cells currently has very few competitors in the market. So this product of ours provides a 3-in-1 suite integrating charging, discharging, and battery cell simulation. All BBU testing stages are within our products. Capability, this is our solution for the BBU market. Meanwhile, the BBU must also satisfy the megawatt-level OCP testing mentioned earlier, which falls under our third scenario. In 25 minutes, I introduced FaithTech's solutions for 5 AI power scenarios. Thank you for listening.